What's up guys, and welcome to this video tutorial. This is part 2 of the root locus series. In the last video we went over just the guides for plotting a root locus, and in this video we are actually going to do an example using those guides. So let's call this example 1. The plan is to try and get through about 3 of these, if not more, just so that you have lots of examples to do. Okay, so example 1. This question says, let's say it's given us the characteristic equation in the format g of s of h of s is equal to k times s plus 2 over s plus 3, s plus 7. Okay, so like we spoke about before, we need to get this into the format that we like, which looks like this, which is 1 plus k over the numerator divided by the denominator. Okay, so we've already got g of s, h of s. So basically all we need to do is the format we want it in is 1 plus k s plus 2 divided by s plus 3 over s plus 7. Okay, so this is the final format that we're going to work with for the characteristic equation. Okay, so guide 1. Okay, so let's say G1. Okay, so guide 1, basically we know it is symmetrical. Okay, we don't need to worry about that too much. Guide 2. Okay, so now we need to work out, using this equation that we have, the poles and the zeros, and where they are equal to 0. Okay, so what we can start off is we look at the numerator, or the top, to see the number of zeros. So we can say that the zeros, let's go to guide 2. Okay, so the zeros, s is equal to minus 2. So for our zeros, we have that as equaling the number of zeros is equal to 1. Okay, the poles, we look at the denominator and we can say that s is equal to 0, or it's equal to minus 3, or it's equal to minus 7. And therefore p is equal to 1, 2, 3, because we have 3 terms here. We've got 1, 2, 3 terms, so p is equal to 3, and therefore we can say that p minus z, which we often need, is equal to 2. So that's 3 minus 1, which is equal to 2. Nothing too difficult there. Okay, so now using guide 2, we know that the number of loci, or the number of parts, is equal to the number of poles. So therefore we can say, so we have 3 poles, so 3 parts. Okay, so basically now we know that we have 3 parts, but at the same time we know we only have 1 0. So that means that one pole ends at a 0. Okay, you don't have to write this down, this is just the thinking that should be happening. One pole ends at 0, and 2 poles end at infinity. Okay, so now that we have this basic information, I'm actually going to plot out a bit of a graph. Okay, let's plot somewhere here. Let's see if I can get a nice, let's see, insert, let's see, shape or something. There we go. Okay, so let's have an axis right here, and we have an axis. Nope. Let's get that. Okay, and let's plot out what we have, the information we have right now. Okay, and let's do the plot in black for now. Okay, so my 0 is at minus 2. Okay, so let's say that every 2 blocks is going to be 1 unit. Okay, and we'll follow the same scale above and below. Okay, I'm just going to draw, okay, I'll draw them both actually, seeing as we know that they're symmetrical. If I need to, okay. So basically the first point is we have s equals -2, so that's -1, so -2 would be here, and that is a 0. So we're going to draw a nice circle there. Okay, let's do that. Okay, so we have a 0 at -2. Okay, and then we have poles at 0, -3, and -7. So 0, 1 right there, -3, so that's -2, -3 is 1 right there, and -7. So -1, 2, 3, 4, 5, 6, 7. -7 would be right here. Okay, so now we have the basics of what's happening, or we know where all our points are. And as we can see, we've got 3 poles and 1 0. Okay, cool stuff. So we've done guide 2. Guide 3, we can move on to guide 3. Guide 3 basically says that our root locus exists between these. Okay, so our root locus exists. I'm going to draw the root locus in purple now. Okay, let's actually, not purple, but let's try a different color. Let's make it a bit thicker. Okay, so this is what our root locus looks like. It exists here. Okay, and we know that it goes from a pole to a 0, and it terminates at that 0. And the root locus exists somewhere between these 2 poles. Okay, but we know that it goes to infinity somewhere, so we know there's going to be a breakaway point, or yes, a breakaway point, and there's nothing to the left of even number of poles, which is guide 4 as well. So guide 3 and 4 we did in one step. Okay, and that has been drawn onto the root locus. Okay, so now what we care about is the breakaway points. So guide 5. Okay, so the breakaway points. Okay, so we need to calculate dk ds. Okay, so what we need to do is get dk or k as a function of s, and we use this equation right here. So let's start off. Let me do the whole thing for you so that you know exactly what's happening in this first video. Okay, so our equation that we have is 1 plus k over s plus 2 over s plus 3, s plus 7 equals 0. Okay, so we take the -1 to the other side, and we're left with k times s plus 2, s plus 3, s plus 7 equals -1. And from this we can say that k is equal to, multiplying up, so it's going to be minus s plus 3, s plus 7 all over s plus 2. Okay, so that is what we have. And then now we have k as a function of s, which is what we need. So now we have to calculate dk ds. Okay, so dk over ds. Okay, so over here we can multiply this out, and that's going to be minus on the outside s cubed plus, what's that, 10s squared plus 21s plus 0 all over s plus 2. Okay, so at this point you have to use okay, and we basically set this equal to 0, so we only care about the magnitude. We don't care about that minus sign in the front, because we set it to 0, and then we have to calculate dk ds using the quotient rule. Okay, so at this point I'm going to assume everyone knows the quotient rule, and I'm going to just say dk ds equals 2 over s cubed plus 8 s squared plus 20s plus 21 divided by s plus 2 all squared, and that's equal to 0. Okay, so this, from here to there, we use the quotient rule, okay, for differentiation. Okay, so now that we've set this equal to 0, basically all we care about is the numerator. So we can say that this, technically this is a minus sign. Okay, so we can keep the minus there, and then what we can do is the minus goes away because of that 0, because we're equating it to 0. So then we also don't care about the denominator. So all we care about is s cubed plus 8s squared plus 20s plus 21 equaling 0. And then what we can do is we can plug this into our calculator and get the roots. So s is equal to minus 4,6906. Or we can say that s equals minus 1,6547 plus minus 1,3187i. Okay, and now what we need to do is we need to figure out, we've got three options essentially, but we need to figure out which ones actually are applicable and which ones are not applicable. Okay, so if we look at minus 4.7 basically, so that would fall somewhere, so that's minus 1, 2, 3, minus 4. Minus 4.7 would be, let's say, somewhere right about there. Okay, so that's actually on our root locus, which would be the most applicable place for it to be. And these ones are actually imaginary, so they would exist somewhere, let's see, minus 1.5 essentially, and minus, so it would exist somewhere, let's say minus 1.5 and minus 1.3 exist somewhere here and here. But obviously we know that it has to exist on the root locus itself, and it can't be imaginary terms. So basically what we can say is that this solution is not applicable. Okay, and therefore the breakaway point is at s is equal to minus 4,6906. Okay, and then if you wanted to calculate the value of k for that, okay, so let's just get that. Okay, so k at s equals minus 4,6906 is equal to, okay, so all we're going to do is substitute into this equation right here the value of s. So that's going to be s plus 3, s plus 7 over s plus 2, and we get that k is equal to 63,0319 to 3 decimal places. Okay, so we know what the value of k is at that breakaway point. Okay, so now it's time to deal with the asymptotes. So we're moving on to, so the answer to this, let's just put it in a box so that we know exactly what we need. Oh, let's just put the entire thing in a box. Okay, so now we can move on to guide number 6. Okay, so guide number 6 has to do with our angle at which they terminate. Okay, so theta equals, okay, so which rule should we use now? Let's use the second one. It's 2k plus 1 over p minus z, 2k plus 1 over p minus z times 180 degrees, where k equals 0, 1, 2, all the way to p minus z minus 1. Okay, p minus z minus 1, we already know p minus z is 2 minus 1 is 1. So this value here is 1. So therefore k is equal to 0 and k is equal to 1. Okay, so we start off with theta is equal to 1 over 2 times 180 degrees. If that's correct. Yeah, so that's 90 degrees. And then theta is equal to, so it's 2 times 1 plus 1, divide all of that divided by 2. So it's 3 over 2 times 180 degrees, which is equal to 270 degrees. Okay, so that is our angle. So we know what the angles are going to be. So they're going to break away at 90 degrees and 180 degrees. Okay, and the way that we measure this is we say that this is the real, this is the imaginary, and we say that this is 0, this is 90 degrees, this is 180 degrees, and this is 270 degrees. Okay, so that's how we get the angles. So basically what we're saying is we're going to break away at 90, so straight up, and at 270, which is straight down. Okay, and now we can go to rule number 7, or guide number 7. Guide number 7 says sigma, or our breakaway point, or the point of the asymptote, the centroid of the asymptote, is equal to the sum of the S values of the poles minus the sum of the S values of the zeros all over the poles minus the zeros. Okay, we already know that the pole minus the 0 is 2. Okay, so sum of the poles. So sum of the poles are the sum of these values right here. So what we're going to have is 0, minus 3, minus 7, minus the sum of the zeros, which is the sum of this right here. Okay, so minus 2. So that is going to be minus 8. Okay, so that's going to be minus 8. Minus 8. Okay, let's just write that out just for anyone who's confused. So what we have is 0, minus 3, minus 7, minus 2, which is minus 8 divided by 2, which is equal to minus 4. Okay, so now we know exactly where the asymptote breaks out as well. Okay, so let's go put that in nicely. Okay, so let's do the asymptote in black. Okay, so this is minus 1, minus 2, minus 3, minus 4. Minus 4 looks like this. Okay, and what we're going to do is we're going to have asymptote right here at 90 degrees. That there is 90 degrees, and straight down at 200. That there was 270 degrees. Okay, and basically what we know is that from this breakaway point, it's going to go to infinity along the asymptote, right? So what it's going to look like, and they break away at 90 degrees. Let's see if I can get this nicely. So when it breaks away, it's going to look something like that. Okay, and it breaks away, and it's symmetrical. So let's try to get that as symmetrical as we can, and it breaks away along that axis all the way to infinity. Okay, and what we can say is we know, okay, let's clean that up there. We know that the direction is it's going to want to go inwards, and they want to go away from the poles. Okay, so now we have that drawn out nicely, and the last thing that we need to do is guide number 8. However, as we can see from the graph that we've drawn, the actual root locus, this root locus is now complete. The root locus never intercepts with the imaginary axis anywhere, so basically we don't need to carry out guide number 8, but what we can do is we can put the values of S. So the breakaway point was at minus 4 point, let's say 7, minus 4.7, so let's go label that point right there. That point right there is S equals minus 4,7, and it was at K equals 63, if I'm correct. Yeah, 63. Okay, and these points were K equals 0. All of these points are K equals 0, K equals 0, and K equals 0 at all of these. Okay, but we don't really care about those because the most important one is that K equals 63, because that's where it breaks away. Okay, and like I said, we don't need to go into guide 8. If for some reason this graph looks something like that, then we would need to go into guide number 8 to see what the value of this point is right here in order to say whether it's stable or unstable. But this particular situation, it's stable all the time because it doesn't ever cross the imaginary axis. Okay, so in the next video, we will do something maybe a bit more challenging where we actually have to go into guide number 8. But this was a very nice introduction, I think, for everyone just to see how the guides work. Okay, so thanks for watching, guys. I hope you guys found this useful.